In this video, we are going to discuss Cauchy-Schwartz inequality for real numbers. But before stating the Cauchy-Schwartz inequality, let's consider four real numbers, say a1, a2 and b1, b2. Now consider the term a1 square plus a2 square multiplied with b1 square plus b2 square. After multiplication, you can get this is equal to a1 square plus b1 square plus a1 square into b2 square plus now a2 square multiplied with b1 square plus a2 square multiplied with b2 square. Now what will I do? I'll combine this term with this. So I will have a1 b1 here and a2 b2. So all the four real numbers are involved in these two terms. Similarly, in these two terms, a1, a2, b1, b2, all four numbers are involved. So I will write it as a1 square into b1 square plus this I will write it as a2 square plus b2 square. And then I will have a1 square into b2 square plus a2 square into b1 square. Now I will try to make it complete square. So with this term a1 square b1 square plus a2 square b2 square, I'll have to add 2 times a1 b1 into a2 b2. Then I'll remain with this term plus a1 square into b2 square plus a2 square into b1 square, and since I have added 2 times a1 b1 a2 b2, to balance it I'll have to subtract 2 times a1 b1 a2 b2. And now you can see this term will give you a1 b1 plus a2 b2 complete square, and this remaining term a1 square b2 square plus a2 square b1 square minus 2 a1 b1 a2 b2 will give you a1 b2 minus a2 b1 complete square. From here you will have a1 square plus a2 square into b1 square plus b2 square minus a1 b1 plus a2 b2 square is equal to a1 b2 minus a2 b1 square. And since right hand side is complete square, it is greater equal 0. Therefore you have a1 square plus a2 square multiplied with b1 square plus b2 square minus square of a1 b1 plus a2 b2 is greater equal 0. And that will imply a1 square plus a2 square into b1 square plus b2 square is greater equal square of a1 b1 plus a2 b2. That means you have a1 b1 plus a2 b2 square is less equal a1 square plus a2 square multiplied with b1 square plus b2 square. So I considered two sequence of real numbers, one a1 a2 and second was b1 b2, and I got this inequality. Now naturally, next question which I will ask, can I extend this idea to sequence of three real numbers? That means if I have real numbers say a1 a2 a3 and b1 b2 b3, can I say a1 b1 plus a2 b2 plus a3 b3 complete square is less equal a1 square plus a2 square plus a3 square into b1 square plus b2 square plus B3 square. So my question is, can we say this? Let's try to see it. Again consider the term a1 square plus a2 square plus a3 square multiplied with b1 square plus b2 square plus b3 square. If you multiply it, you will have a1 square into b1 square plus a1 square into b2 square plus a1 square into b3 square. Then a2 square into b1 square plus a2 square into b2 square plus a2 square into b3 square. Then a3 square into b1 square plus a3 square into b2 square plus a3 square into b3 square. Now from here again combine these terms a1 square b1 square plus a2 square b2 square and a3 square b3 square. So let's combine it. So I will have a1 square b1 square plus a2 square b2 square plus a3 square b3 square. And I would like to make it complete square. So I will add 2 times a1 b1 into a2 b2 plus 2 times a1 b1 into a3 b3 plus 2 times a2 b2 into a3 b3. So this total will give you complete square of a1 b1 plus a2 b2 plus a3 b3. Now after this what I am having, I will remain with these 6 terms, that is a1 square b2 square plus a1 square b3 square plus a2 square b1 square plus a2 square b3 square plus a3 square b1 square plus a3 square b2 square. And since I have added these 3 terms 2a1 b1 a2 b2, 2a1 b1 a3 b3, 2a2 b2 a3 b3, to balance it I will have to subtract these 3 terms. So it will be minus 2a1 b1 a2 b2 minus 2a1 b1 a3 b3 minus 2 times a2 b2 a3 b3. Now let's see how we will combine it. So this term will give you a1 b1 plus a2 b2 plus a3 b3 complete square. Now what will I do? Since I here have a1 b1 a2 b2, so if I see this from here I will have a1 b2 and from here I will have a2 b1. So I will combine these two terms. So I will have a1 square b2 square plus a2 square b1 square, and I'll combine it with this term, that is minus 2 times a1 b1 a2 b2 plus this a1 b3 I'll combine it with a3 b1, and from here I will have minus 2 times a1 b1 a3 b3. So what I'll get is a1 square b3 square plus a3 square b1 square minus 2 times a1 b1 a3 b3. Then I remain with this term a2 square b3 square plus this term a3 square b2 square and then minus 2 times a2 b2 a3 b3, and this you can say is equal to square of a1 b1 plus a2 b2 plus a3 b3 plus this term is equal to a1 b2 minus a2 b1 square. This term is equal to a1 b3 minus a3 b1 square, and the last term is equal to a2 b3 minus a3 b2 complete square. So what you have got, a1 square plus a2 square plus a3 square multiplied with b1 square plus b2 square plus b3 square is equal to a1 b1 plus a2 b2 plus a3 b3 complete square plus a1 b2 minus a2 b1 square plus a1 b3 minus a3 b1 square plus a2 b3 minus a3 b2 square. And from here you will get a1 square plus a2 square plus a3 square multiplied with b1 square plus b2 square plus b3 square minus square of a1 b1 plus a2 b2 plus a3 b3 is equal to a1 b2 minus a2 b1 square plus a1 b3 minus a3 b1 square plus a2 b3 minus a3 b2 square. Since right hand side is addition of three complete square terms, it is always greater equal 0. And that will imply a1 square plus a2 square plus a3 square into b1 square plus b2 square plus b3 square is greater equal square of a1 b1 plus a2 b2 plus a3 b3. That means you have got a1 b1 plus a2 b2 plus a3 b3 complete square is less equal a1 square plus a2 square plus a3 square multiplied with b1 square plus b2 square plus b3 square. So what we have observed, when we had only sequence of two real numbers a1 a2 and b1 b2, there we got a1 b1 plus a2 b2 complete square is less equal a1 square plus a2 square into b1 square plus b2 square. And here when I had sequence of three real numbers, I got a1 b1 plus a2 b2 plus a3 b3 square is less equal a1 square plus a2 square plus a3 square into b1 square plus b2 square plus b3 square. So naturally, the next question which I will ask, can we extend this idea for two sequences of n real numbers? That means if I have two sequences, say a1 a2 an and b1 b2 bn, can I say a1 b1 plus a2 b2 plus an bn, its complete square is less equal a1 square plus a2 square up to an square multiplied with b1 square plus b2 square plus bn square? And the answer is yes, we can have this inequality for two sequences of n real numbers. And this inequality is precisely your Cauchy-Schwartz inequality. Let me formally write it now. So your Cauchy-Schwartz inequality states that if a1, a2, an and b1, b2, bn are two sequences of real numbers, then from here you can see it is square of a1 b1 plus a2 b2 plus an bn. So I will write it as summation of ai bi I running from 1 to n and its complete square is less equal a1 square plus a2 square plus an square, that I can say is equal to summation of ai square I running from 1 to n multiplied with b1 square plus b2 square plus bn square, that I can write it as summation bi square I running from 1 to n. So this is our Cauchy-Schwartz inequality. We will give two different proofs for this inequality. Let's see the first proof. So first, consider the term summation aibj minus aj bi square, where first your j is running from 1 to n and then your I is also running from 1 to n. So this term is equal to summation ai square bj square plus aj square bi square minus 2 times ai bj into aj bi, where our j is running from 1 to n and then our I is also running from 1 to n. Now this I can say is equal to summation ai square into bj square, j running from 1 to n and I running from 1 to n, plus summation aj square bi square, j running from 1 to n, I also running from 1 to n, minus 2 times summation ai bj into aj bi, j running from 1 to n, I also going from 1 to n. Now observe the first term. Here first I will be fixed and j will be running from 1 to n. So the terms will be like ai square multiplied with b1 square plus ai square multiplied with b2 square plus ai square multiplied with b3 square. In this way you will go up to ai square into bn square. So you can say it is ai square times summation of bj square, j running from 1 to n. Similarly, now your I will also be running from 1 to n. So you can say this term is equal to summation of ai square I running from 1 to n multiplied with summation bj square j running from 1 to n. In the same way, your second term is equal to summation aj square j running from 1 to n multiplied with summation bi square I running from 1 to n. And this term I can say is equal to minus 2 times summation. Now I will combine ai and bi multiplied with summation. Now remaining term is aj and bj. Here j is running from 1 to n and here I is running from 1 to n. If you closely observe, the first two terms are actually same. See here, it is summation ai square I running from 1 to n. That means it is a1 square plus a2 square up to an square. Similarly, here it is summation aj square. That means it is a1 square plus a2 square up to an square. Similarly, summation bj square j running from 1 to n is same as summation bi square I running from 1 to n. So you can say it is equal to 2 times summation ai square I running from 1 to n multiplied with summation bi square I running from 1 to n. Also, in the last term, if you see, summation ai bi I running from 1 to n is equal to a1 b1 plus a2 b2 up to an bn, and this term summation aj bj j running from 1 to n is also equal to a1 b1 plus a2 b2 up to an bn. So both the terms in this last expression are same. Therefore, you can say it is equal to minus 2 times summation ai bi I running from 1 to n and its complete square. So let me summarize it what we have got till now. We started with our expression summation ai bj minus aj bi complete square, where first j was running from 1 to n and then I was going from 1 to n. And then I got this term is equal to 2 times summation ai square into summation bi square minus 2 times summation ai bi complete square, everywhere I is going from 1 to n. Now if you see this left hand side, it is addition of complete square terms. Therefore, this quantity is greater equal 0. And hence it will imply your right hand side is also greater equal 0. And from where you can get 2 times summation ai square into summation bi square I running from 1 to n is greater equal 2 times summation ai bi complete square I running from 1 to n. And then by multiplying with 1 upon 2 on both the side of inequality, you will get summation ai bi complete square I running from 1 to n is less equal summation ai square I running from 1 to n multiplied with summation bi square I running from 1 to n. And this is precisely your Cauchy-Schwartz inequality. So we have given one proof for Cauchy-Schwartz inequality. Let's try to give a different proof now for the same Cauchy-Schwartz inequality. So I'll say second proof. Now here I will use little bit of calculus and my job will be much easier than what we did in our first proof. So now let's first see what are the terms involved in our Cauchy-Schwartz inequality. If you see, here you have summation ai square I running from 1 to n. Say I will call it as capital A. Then here you can see you have one term summation ai bi. So I will call this summation ai bi I running from 1 to n as b. Then one more term is involved, that is summation bi square I running from 1 to n. I will call this term as capital C. Now consider a function f of x given by ax square minus 2bx plus c. You can say this is a quadratic polynomial in x. And this is equal to summation ai square I running from 1 to n times x square minus 2 times summation ai into bi I running from 1 to n into x plus summation bi square I running from 1 to n. This you can say is equal to summation ai square x square minus 2 times ai bi x plus bi square, where I is running from 1 to n. Now you can observe that this term in the summation is a complete square. It is ai square x square plus bi square minus 2 times ai bi x. So you can say it is equal to summation aix minus bi complete square I running from 1 to n. Now it is addition of complete square terms, so this is always going to be greater equal 0. So you started with a polynomial of degree 2 f of x given by ax square minus 2bx plus c, and you got this second degree polynomial always assumes value greater equal 0. Now you know that a degree 2 polynomial represents a parabola, and since this degree 2 polynomial always assumes value greater equal 0, this parabola lies above your x-axis, or at most it can touch your x-axis. Now you know if it lies above x-axis, it does not have any real root, and in that case discriminant of this polynomial is strictly less than 0. And if your parabola touches your x-axis, that means your quadratic polynomial has repeated roots, and in that case discriminant of your polynomial is equal to 0. So you have discriminant of f of x is less equal 0. And what is discriminant of f of x? It is square of coefficient of x, that is 2b square minus 4 times coefficient of x square into constant, that is ac, and it is less equal 0. From here you will get 2b square is 4 times b square minus 4ac is less equal 0. That means 4b square is less equal 4ac. And then after multiplying by 1 by 4 on both the side of inequality, you will get b square is less equal a into c. And what is your b square? It is square of summation aibi I running from 1 to n. And what is a? Is summation of ai square I running from 1 to n, and it is multiplied with c, which is equal to summation bi square I running from 1 to n. And this is precisely your Cauchy-Schwartz inequality. So we have given two different proofs for our Cauchy-Schwartz inequality of real numbers.